Okay, so what is a coupling kernel? When I was trying to come up with a way to interact with systems of coupled oscillators in a reliable, predictable way without having to train sophisticated neural networks, control systems or mechanisms, or really for that matter, to hard code specific geometries of the network for particular control systems. Like, no, I wanted a way of interfacing with a system of coupled oscillators that was very natural and very, very bottom up, but reliable and predictable. What I ultimately arrived at by coding dozens of systems of coupled oscillators and trying to wire them in different ways, the first thing that really emerged clearly was starting to replicate some psychedelic phenomenology to some extent, was Kuramoto oscillators, and then geometrizing them in a traditional system of coupled oscillators, at least in the classic formulation of Kuramoto oscillators. What you have is kind of like an all-to-all relationship, where like every oscillator is connected with every other oscillator. Then they're all trying to be in phase with each other. And when they're out of phase with each other, there's kind of like an error. They're all kind of like moving around in a circle. Or you could even think of it as, for example, like metronomes in a table or something like that, tuned to slightly different natural frequencies. They actually want to oscillate at slightly different speeds, but because they all belong to the same table, they're all on the same ground, as it were, there's tiny vibrations that are actually shared between them. With those tiny vibrations, they are kind of like pulling and pushing each other. In the classic formulation of Kuramoto systems, they're all connected to each other and equally connected. And then there's some fascinating mathematics that you can show analytically. There's like some convergence conditions that under certain circumstances, all of the oscillators actually click together. They all kind of end up being dragged along by what's kind of the mean of the phase of all of the oscillators. What's nice about it is very tractable. It's not even trying to accurately model some physical systems of oscillators. It's more kind of like a mathematical abstraction that just works very nicely. In the realm of phenomenology, we're talking about these very complex networks. Like your visual cortex, your vasculature, your somatosensory cortex. You have a lot of different networks connected in different ways. It's not the case that all of the oscillators are connected to each other. Instead, it's actually some kind of like geometric embedding. All of these oscillators are in some kind of geometric space. Whether they're two oscillators are connected or not, it's kind of like a function of their distance. There might be like a simple rule, something like if two oscillators are within a certain distance, then there is a connection between them. And if they're further away than that distance, then they're not connected. So in that way, you kind of like represent a geometric space in terms of some kind of like connectivity between systems of coupled oscillators. What I stumbled upon by playing with these systems was, well, maybe we can actually modulate what's called the coupling constant between oscillators at different distances. And maybe that way we can gain some control over kind of like the overall, emergent oscillations that happen at the macroscopic level. So, it looks something like this. In some of the simulations that you will see, for any given oscillator, if you look at oscillators at distance 1 from it, especially if it's, let's say, a square lattice, there's going to be 4 oscillators at that distance. And so there's a lever that, depending on the value that you set it up at, is going to modulate a positive or negative coefficient for the coupling constant for oscillators at that distance. This is called Manhattan distance, which is add up the distance in the x-axis and the y-axis. They call it Manhattan distance because it's sort of like the number of blocks that you would have to go from one place to another in a city grid. You don't care about like the diagonal distance, you care about like the streets and avenues added together. And then at a distance 2, this, let's say, intersection, it starts to actually form kind of like a diamond shape. Now you have like 8 oscillators at distance 2. And there's going to be a lever that modulates the coupling constant to those 8 oscillators. And then there's going to be 12 at distance 3, and 16 at distance 4, and so on and so forth. The central idea of a coupling kernel is a system of levers that modulate the coupling constant of the oscillators for each of those different Manhattan distances. Well, it doesn't have to be Manhattan. This is just in a square grid. If we're talking about a 3D continuous space, and a lot of our simulations are like that, then it can be Euclidean distance. It can also be like distance in other geometries. It could be on the surface of a sphere. It could be in a hyperbolic space. This is very general. For the sake of simplicity, in a square lattice, we're talking about x plus y in terms of like the streets and avenues. If you play with this system, you will realize that coupling kernels as neural global bridges. Even before I go there, I'm going to explain briefly what a small world network is, because there's another lever that we usually also include. At the beginning of a simulation, essentially what we do is like for every given oscillator, we choose two other oscillators at random in the entire grid, and we wire them to it. And then the small world lever is going to be modulating effectively the coupling constant to those two at random. Which, it's effectively is a random network. And we call it small world because what is very well known, the social distance between people, it's actually pretty small on average, between you and the Queen Elizabeth. Chances are you know somebody who knows somebody who knows somebody who knows somebody who knows that person. The number of hops that you need to take between you and that person usually doesn't go above 6. There's such a thing that is called the diameter of a graph, which is like what is the longest, the shortest path. What is the pair of nodes such that the shortest path is the longest? What happens is that if you have a kind of this network that is geometric, where nodes are connected to their neighbors or neighbors within a certain distance, the diameter is very large because you actually have to walk in that world, embedded in a geometric space. And in the medieval time or earlier, before there were kind of like these long distances that people were traveling, yes, the social distance between individuals was pretty large, but not anymore. No, there was kind of like a threshold in social evolution where enough people were making long trips that is effectively adding this random network on top of a geometric network. And when you do that, then you shrink the diameter and you turn it into a small world. So you don't actually need many random connections. There's kind of like a threshold, a percentage of random connections where the diameter completely collapses and then like everybody is right next to everybody else. That's one important way of modulating the activity of the system of coupled oscillators, is adding this small world network, which is effectively a way of either scrambling the activity when the coupling coefficient is negative in the small world network, or a way of synchronizing everybody when it is positive. Significantly increase the state space of configurations accessible with this lever system. Let's just focus for a moment on the geometric components, the coupling 1, coupling 2, coupling 3, and 4. One thing that I did was apply what is called a discrete cosine transform. The discrete cosine transform is a Fourier transform. And effectively what you're doing is showing in what way waves of different spatial frequencies, a wave with a low spatial frequency is a wave that is very large. A wave with a high spatial frequency is a very intricate, detailed wave. You can essentially tune into global resonant modes of the entire system of coupled oscillators by just modulating the coefficients of the coupling kernel. It turns out that you can actually rigorously prove this to be the case with techniques from a field that's called a spectral graph theory. You effectively apply filters on a graph for different distances. Effectively what's called the various powers of the Laplacian of the system effectively will be modulating the amplitude for different resonant modes of different spatial frequencies. We just kind of stumbled upon this way of modulating the amplitude of the energy for waves of different spatial frequencies. Systems of coupled oscillators, they're considered very complex systems. These very intractable, hard to predict dynamic systems, and the fact that you can actually tune into global resonant modes of them just by modulating the amplitude of a coupling kernel is utterly fascinating. It gives you a handle with predictable effects and predictable resonance effects that are holistic and global of the entire brain, or the entire graph in this case, by just modulating the amplitude on levers. That was pretty mind-blowing and pretty important for me, a milestone really in how to make sense of complex systems of coupled oscillators. Well, it turns out that November of last year at a work retreat in Tepoztlán with other people at QRI, we encountered a paper by Marco Aquil. I went to his thesis defense and he presented at the Amsterdam QRI meetup. That was actually super awesome. This is his thesis called Levels of Vision. He touches upon some of these key pieces of the puzzle, which is called divisive normalization. He developed a method called chaos with two S's, which effectively is a way of analyzing the resonant modes of a brain in terms of modulating kind of something that is very mathematically equivalent to something like a coupling kernel. To me, that was mind-blowing. Oh my gosh, actually in academia, they're arriving at something quite similar from a very different perspective. From our perspective, we're taking phenomenology seriously. We're trying to replicate the features of different exotic states of consciousness by using graph theory and dynamic systems and so on. And in this case, they're primarily actually not so much actually trying to replicate phenomenology. They're trying to replicate psychophysical measurements and neuroscientific measurements, neuroimaging data sets. It is kind of like the objective scientific measurements of the brain from a third-person perspective, all of a sudden arriving and converging into very similar ideas and very similar models to QRI, who is effectively championing taking phenomenology seriously and bringing advanced meditators and physicists and mathematicians and visual artists to depict and make sense of exotic states of consciousness. Yeah, chaos effectively, kind of like converges in very similar ideas. Just to recap, coupling kernels are this bridge between neural activity and global activity.